Okay, well, first of all, let me give my sincere thanks to Renzo for organizing this fantastic conference. It's been at a really high level, at least until now. But fortunately, I do have some excellent collaborators that will keep me on the straight and narrow. So these are Daniel Faraco, who's at ICMAT, Solly Lindberg, who's in Helsinki, and Alberto Valli, who's in Trento, which is at the other end of Italy. So this project began when I was visiting Alberto in Trento, and as usual, we were planning to do something else, and then we were both stood in front of a blackboard, unable to agree on a definition of helicity. So this is where this work kind of came out of. And at the same time, Daniel and Solly were making great strides in some aspects of turbulence theory. And it turned out that the work we were doing fitted very well together. So it was a happy coincidence. Okay, there's quite a lot of backstory that's required to understand this topic. And I've tried to, I'm going to try and present it with as few prerequisites as necessary. So hopefully everybody should get something out of this talk. So first of all, I need to describe something called Vulture-Taylor theory, which is actually about an experiment and the theory to describe that experiment, which is the source of what I'm talking about today. Then I will take a little excursion into a kind of a topological description of helicity, and then I'll use that to go into some turbulence modeling and then prove this result, which is known as Taylor's conjecture. Okay, so first of all, let's focus on the experiment. Okay, so we're talking about plasma physics here. So for the purposes of this talk, you can just think of a plasma as an electrically conducting fluid, which is permeated by a magnetic field. The flow can deform the magnetic field, and the magnetic field can deform the flow. Okay, so there's a nonlinear interaction between the two. And so what I'm about to describe is a reversed field pinch experiment. So basically, you just think of this as plasma in a torus. So it's called a pinch because when you have curved magnetic field lines, there's an associated tension with this, and this force effectively pinches in your plasma and stops it, destroying your laboratory. And what they do in this is a very hand-wavy description, but it's got the key parts, is that they wire perturbation, okay, by changing the voltage essentially in a small gap. And what they're effectively doing is specifying the helicity, okay, of the magnetic field in this domain. Then once they've applied the perturbation, instabilities develop, and so does turbulence. But there's nothing to maintain this turbulence, so eventually it relaxes down. And what they find at the end, the magnetic field, is that, well, I kind of jumped the gun here because what they measure, at least, is that they have something which is very similar to something called a linear force-free field. Now, this is where a linear force-free field is where the curl of the magnetic field, which is like the current density, is equal to some linear constant times the magnetic field. Okay. Now, in order to describe these results, a plasma physicist called Brian Taylor came up with this theory, and I've kind of split it into two key parts. The first part is conjecture that global magnetic helicity is conserved in a weakly resistive plasma. Okay, so when turbulence develops in this stage, the magnetic field lines are reconnecting everywhere. Okay. And Taylor argued with some physical arguments that although in theory you can define an infinite number topological invariance, which would be invariant in a non-resistive plasma. The only one that actually survives is the global magnetic helicity. Okay, so I've called Taylor's conjecture the conjecture that global magnetic helicity is conserved in such a plasma. Now, it's slightly controversial whether or not that's the only topological quantity which is conserved. However, other people, I believe, are going to talk about this, so I won't mention it further. The second part was that, given this, Taylor used a theorem that had been proved in the late 50s, called Volcher's theorem, which basically says that if you have a magnetic field which is minimized subject to constant global helicity, then the result is a linear force-free field. And a linear force-free field matched the data that they found in the experiment very well. So Taylor put these two things together, and we have Volcher-Taylor theory. Now, over the years, of course, there have been many criticisms of this theory. However, I still think it's one of the it's a remarkable theory, because there are very few instances in the history of the theory of turbulence where you can write down the final answer, and you can do it here. Okay, so let's consider a magnetically closed domain, okay, which is one where we have, if n is the normal vector on your boundary, which is a b dot n on the boundary. And we're basically interested in showing this thing here. So you've seen this earlier in the week, that the integral over the domain of the magnetic field, which is a divergence-free vector field, dotted with its vector potential, so curl A is equal to B, basically that's not changing in time. This is effectively what we want to show. Now, in simply connected domains, we have various results. Okay, for laminar and ideal flows, this is something that undergraduates prove, and this is what we mean by an ideal invariant. Effectively, the magnetic field lines behave as material lines in the fluid, and they never reconnect. Okay, so you can preserve various topological structures. Then Mitch Berger, in the mid-80s, derived bounds on the helicity. Now we're talking about the magnetic field with some diffusion, so a resistive plasma, and he found bounds in relation to the energy. So basically, the energy changes a lot faster than the helicity. Now, strictly speaking, he was showing this with something called relative helicity, but for the purposes of this talk, that's just a technicality. Okay, and finally, very recently, Fracco and Lindberg proved this result for turbulent flows. Okay, and I'll go into more detail on this later. Okay, so what if omega is multiply connected? Okay, so all these results were simply connected. Now we have to consider multiply connected domains because the experimental setups are multiply connected. And of course, in the past, people have looked at helicity in multiply connected domains, including several people in this room. And what they've done is they've chosen a particular gauge. So normally for this kind of classical helicity, they've chosen something called the Biot-Savart gauge, which Mitch showed earlier in his talk. Now, this is a useful thing to do, and indeed, this is what Moffat originally did in order to make the link, pun absolutely intended, to helicity and the linking number. So Mitch also mentioned in his talk that the A was a dirty word, and what I want to try and do today is rehabilitate A somewhat by showing that even with a general vector potential, you can get the topological interpretation of helicity as well. At least that's one of the things I want to show. Okay, so we seek a general definition of magnetic helicity. So one that satisfies any vector potential, or to be more specific, one that satisfies the vector potential in this set here. So curl A dot n equal to 0 on the boundary. That's just B dot n equal, of course, on the boundary. Okay. Now, since we're dealing with vector potentials, of course, we need to make sure that an expression that we have is gauge invariant. Okay. Now, in a simply connected domain, this is quite simple. Again, this is an undergraduate calculation, but it's worth showing here to try and frame our way of thinking about this. So I consider some new vector potential A prime, which is just my old A plus the gradient of some scalar function. Okay, and then if I if I dot them with B and integrate them, I can see that this helicity here is equal to this helicity here plus some leftover term. Okay. Now that leftover term, just with some simple operations, I can push to the boundary. Okay, and I show that it's 0. So normally one thinks of this leftover term as just you know, an annoyance, in fact, that's preventing you having this equal to this. But what I want to show today is that actually there's important topological information trapped in this leftover term, and we'll see that when it comes to, in particular, when it comes to the multi-valued case. Okay, so actually, let me go back a second. Before I go on to that, I should probably say that you know, what have plasma physicists been doing in the past in tokamaks, which are tori. So when they actually calculate helicity, they normally don't use Biot-Savart because although that's useful for theoretical devices, it's not so handy for practical calculations. So they'll choose some vector potential, which is more helpful to them. And what they do is they apply this kind of operation here. But of course, in a torus, this means that this term here becomes multi-valued. Okay, and so they do the thing which Renzo described in the first talk of this conference about jumping over, cutting the domain so it becomes simply connected and then jumping over it. Okay, and so they get some extra term. However, we weren't. What we wanted to do was kind of generalize this to effectively any domain with or any closed domain with effectively arbitrary topology. Okay, because there are other domains even used in plasma physics for which it's a bit tricky to generalize using this approach here. So what we wanted to do was basically keep things single valued. Okay, and the way to do that really is to recognize that Helmholtz theorem in a closed domain is made up of 3 parts. So in a simply connected domain, you can write a vector as the curl of something plus the gradient of something. But we also have this extra vector here, which is a harmonic field. Okay, so this is the set of harmonic fields defined here. And if you write the magnetic field like this, then these 2 terms are now single valued. And effectively, you're kind of pushing the multi-valuedness into this vector here. And we know that multi-valuedness is related to topology. So somehow this is going to tell us about the topology of the domain. So we need to work a bit on that in order to derive a result for helicity, which is true for any topology. Okay, so let me. I thought I would just show this via pictures rather than writing out a whole list of definitions. So here we have a torus with 2 holes, genus 2, and what I've drawn. So this is our domain omega, if you like, and what I've drawn here are cycles, which are you know, not bounding in omega. Okay, so cycles which are picking out the holes. And if you like, these represent the generators of the first homology group of this, this domain here. Similarly, we can take a ball around this domain and then cut it out so that this domain now becomes the hole in the ball. And we do the same thing and we get the cycles of our complementary domain, which are these red arrows here. Now, these cycles create cutting surfaces in the opposite domain. Okay, so the primed ones, which are from the cycles in the complement domain, create cutting surfaces in omega, and vice versa here. Okay, so we can use these to describe the space of harmonic functions, which we need to use to work out our helicity. Okay, so this space here is finitely generated, okay, by these vector fields here. Okay, there's G of them corresponding to the genus, and similarly we can do this. Oh, I'll put this one. Hello? Okay. So we can, okay, so we can define these spaces for our domain and the complement of the domain, okay, and we can define them by imposing these conditions here. If you like, these are related to the generators of the first de Rham cohomology group for this domain here. But the take-home message, if you like, is the fact that we can, this extra space that we introduced, the space of harmonic functions, we can define a basis for it, and that basis is related directly to the topology of our domain. Okay, here's another example of a multiply connected domain, one which is more practical use for plasma physics. So this is a toroidal shell. So you just see the toroidal shell cut in half. And so this thing inside is a hole. This is slightly more complicated than the one before because now you can see the cycle here is not connected. So this is one cycle, these two circles here. However, that's no real problem for the construction that we're doing here. So we can basically consider fairly arbitrary topologies, although of course not all of these are going to be of practical use for plasma physics. Okay, so for defining the magnetic helicity and multiply connected domains, I'm going to, remember I said before for the simply connected case, we kind of compared two different helicities and then there was this leftover term. So I'm going to write down two helicities here. The only difference is the vector potential in each. Now, in general, in multiply connected domains, these should be different. So after some rather simple calculus, I can basically work out what the leftover term is, and it's something that I can shove to the boundary. Okay, it's given by this thing here. So what I need to do now is try and relate that to the basis functions that I found for the harmonic space of harmonic functions from before. Now, you can see here I'm on the boundary. If I focus on this term here, which is and look at the tangent, which are the tangential traces, I can show, I'm not going to show the details, I'm just going to show the result here, that I can express these in terms of the basis vectors for the harmonic space. Okay, so involving both those of my domain omega and of the complementary domain. Okay, and these are just numbers here, which after a little bit of work I can calculate. So after some manipulation, I could show that the leftover term can be represented as this this sum here. Okay, where these numbers here are related like this. So now I've got this term relating to the cycles, okay, of the first homology group of the domain and of its complement. Now, since a cycle in the complementary domain bounds one of the surfaces in the domain omega, then I can apply Stokes' theorem, and for beta j, okay, it's just very simply the flux through this interior cutting surface. And I can do exactly the same thing for mu here. Okay, so putting this all together, I have my difference of helicities, so these two things here, and then this is what the leftover term looks like. But you can see quite clearly that this quantity here is independent of the choice of vector potential, okay? Just by inspection here. And so if I now define this as my gauge-invariant helicity in multiply connected domains, then everything remains single-valued. And now the topology of helicity is coming in directly from its domain. Okay, so hopefully A is slightly rehabilitated here. And clearly, if I go down to 0, then I just get the classical helicity, which is used in the community generally, and yeah, so it's very easy to generalize this to any topology. Okay, so that was how to write down helicity for multiply connected domains. Now I'm going to go and describe some, very briefly, some kind of results from turbulence theory for MHD. And these are the MHD equations. So if you've never seen these before, these are basically the same as the Navier-Stokes equations, except now we have, in the momentum equation, we have this Lorentz force here. And we also have an extra equation for the magnetic field called the induction equation. Okay, so you can see here that there's a nonlinear connection between the magnetic field and the flow. These are the diffusion terms. So this is the resistivity. So when I talk about a weakly resistive plasma, I mean a small value of eta here. This is the viscosity. And again, we're going to be considering small values of this. I'm considering here incompressible flow. Okay, so normally there should be a density in here, but since it's a constant, I've just scaled it to 1. Okay, so to complete this problem, we need, of course, we need boundary conditions. We're going for resistive MHD. Because of the viscosity, we have 0 slip boundary conditions here. And again, we're just considering magnetic surface. When I move to ideal MHD, and in this talk, when I say ideal MHD, I mean both viscosity and resistivity being 0, so no diffusion terms in these equations. Then we have we basically changed a slip condition at the boundary. Okay, so in MHD, the dissipation rate is given by this expression here. Okay, so just the mod of the gradient of the field squared, okay, integrated over the domain. Okay, and they're multiplied by their diffusion coefficients. Now for turbulence, what is found in both experiments and in simulations is that in the limit of these diffusion parameters going to 0, this dissipation does not go to 0. It goes to some positive quantity. Okay. And this is known in turbulence as anomalous dissipation. Now, if that's the case, we want to model this, then, well, how can that happen here? Well, it suggests that what we need is for these terms to blow up, and i.e. for there to be some singularity in either or both B and U. Okay. So in other words, this is what motivates us to consider weak solutions as a good model for MHD turbulence and fluid turbulence as well. This is actually a very old idea, which goes back to Onsager in the 40s, but was kind of rediscovered again in the 90s. And now that a whole range of mathematical tools have developed since then, it's now a very active area of research. So here is an example of writing the ideal MHD equations in weak form. So what you do is, so what I've done here is, hopefully I've gotten this right. I've got my my test function here, which I've taken. This is a vector, which I've taken to be divergence free. It's smooth within my domain, has compact support in my domain, and writing it in this way here is good because it pushes all the derivatives onto your test function. Okay, so there are no longer any derivatives on your main fields. Now, again, as I said, this is a fertile ground of research, and looking at various different levels of integrability for these equations, it's actually a very, very tough problem. And if you look in different spaces, you'll get different results. So it's a bit of a difficult starting point for us. If we want to really, if this is to be a good model of turbulence, we need to be able to pick out physically meaningful solutions. So what we're going to do is we're going to seek out a little bit more regularity, and the way to do that, well, there's not, I don't believe there's a unique way, but the way that we'll do it is to look at something called Leray-Hopf solutions. Now, again, these are, Leray was working in the 30s, I think. So the idea that we haven't had rigorous descriptions of turbulence until recently is actually not really true. People have had these ideas for a long time. It's just maybe that it's taken a while for some of the mathematics to catch up with them. Okay, so suppose that we start off with finite energy. We have our initial conditions divergence free. We satisfy the boundary conditions. When you say that UB is a Leray-Hopf solution, if it's a weak solution of the non-ideal MHD equations with these initial data. So basically the equations I had before, but now with also including the diffusion terms in them, and that it satisfies this following energy bound here. Okay, so this is your energy at time t. This is your time integrated dissipation rate. So these two things are less than your initial energy here. And Leray proved that these exist for R3, and then Hopf did it for basically any closed domain in R. And so this is a kind of highlight of the theorem of Farraco and Lindbergh. So suppose you have a sequence of these diffusion terms going to 0, okay, as J goes to infinity. And for each one of these, you can define a Leray-Hopf solution, okay, with these initial data. Okay, so basically one that satisfies the energy bound that I had before. Then you can show these limits in this space here, and these limits in this space here. If you have these conditions, then you've proved that this system conserves magnetic helicity in time. Okay, so that's the result. If you go to, and of course there's 30 pages of detail proving this, but if you go to the paper, you'll see something which is not quite like this. I've tidied it up a little bit, but it's written something like this in their paper. So these Z's here should be, you want these to be helicity. So what have I written here? Well, the first line is related to these Leray-Hopf solutions, okay? And it's saying that, you know, the helicity at some time minus the helicity at time t equals 0 is equal to this thing here. Now, what is this thing here? Well, in the MHD equations, if you work out the time derivative of helicity and you have a non-zero eta, then you basically get this integral here. Okay, so I've just integrated this in time, and so we have this on the right-hand side. Then what this line is saying is the ideal limit of this, i.e. this going to 0 as j goes to infinity, we get this thing here, which just means that the helicity at time t is equal to its original value. Okay. Now, I've called these Z's and I've not called them helicity because what's written in the paper is this thing here. Okay. Which, as you can see, is very similar to what I wrote down before. Except now what they have is they have this A sigma and AH. But all that is the decomposition of the vector potential in terms of the harmonic part and then what's left over. Okay. So if I consider this now and I write it out in this way, you can see that basically I have almost exactly the same formula as before when I worked out magnetic helicity in multiply connected domains. And the only difference is that we now have this A sigma instead of A. However, that's no problem at all because you can show that the harmonic form of the harmonic part of A is just the same as its original value. Okay, so this is just the same as A sigma plus AH, and so we've basically got it because now using the general version of the helicity formula for multiply connected domains, these things cancel. So now we can update the Faraco-Lindbergh theorem to this form here. So suppose now that U and B is a weak ideal limit of the Leray-Hopf solutions, okay, which are these things here. Then the generalized helicity at time t minus generalized helicity at time 0 is equal to this thing that I described before. And then the ideal limit of that, we have the generalized helicity at time t is just equal to its original value. Okay, so as usual, I've gone far too quickly. And basically, you know, I didn't have any, like Paul, I didn't have any references in the talk, but there are loads of references in the papers, and that's probably what you want anyway. So if you're more interested, you can take a look at these works. But I would recommend actually, if you're new to this area and you want to get into it more, I ran a special issue in geophysical, astrophysical fluid dynamics, and Daniel and Solly and Laszlo wrote a paper on some of and part of this work, and also some other work that they've been doing as well. Okay, if you search for this paper just now, unfortunately the third author's name doesn't appear, but I'm currently battling with the journal to fix this. Okay, I'm going to finish up with this quote here by Hermann Weyl, which says that topology has the peculiarity that questions belonging to its domain may under certain circumstances be decidable, even though the continua to which they are addressed may not be given exactly, but only vaguely, as is always the case in reality. So I thought that summed up pretty neatly the kind of work I was doing here. Okay, thank you for listening.